shall I get started? What do I have to do? Are you ready to go, Robert?
Sure. Do you want to start sharing your screen now, and then we'll do the introduction?
Yeah, I introduce you, Neil, in a second. Welcome to yet another academic semester of experimental math seminar. Had been tradition for the last few years to start it with a bang. The one and only Miss Sloane will talk about interesting new sequences. As usual, please unmute yourself unless you have something to say or you want to laugh at Neil's jokes. And then go back and unmute yourself. Unmute yourself. Thank you. Go ahead. Yeah.
Well, as usual, I don't see. Okay, that doesn't seem to be working. All right, so I've got Keynote running here. Maybe if I kill the Keynote, okay, and then I'll start up Keynote again. Okay, there's Keynote. So now Keynote, good. Okay, there. And share. Did that work?
Yeah,
Sure.
but
Playing the slides.
I'm sorry. Can you see, Robert? Can you see my first slide?
Yeah, we see it. Try playing the slides at full screen.
Okay, will do. Okay, and then I have to get rid of this column of faces, which will obscure. So I hover there, I go to More, and I do to hide video panel. Good, okay.
Looks perfect.
Good, and then I can kill little announcements, and here's the talk. All right, excellent. So there's the title. Okay, that was the title. Here's the outline of the talk. I have a few sections. I probably won't have time to do everything, but Daron has kindly said that he may allow me to give another talk in the spring for the topics I can't get to today. There are probably another half dozen not on this list. So I'm going to begin by talking about Scott Shannon's circle counting talk. And they're down. Yes, okay. So you may remember fairly recently, last couple of years, Lars Blomberg, Scott Shannon and I were working on stained glass windows. And the typical question there is you have a square and you have a number of dots on each boundary, and you join every pair of boundary points by a line, by a chord. And this divides up the region, the square, into little regions, and you get a planar graph. And the question is, how many regions are there and how many vertices? And if you started with a circle, that's a solved problem. But if you start with a square, it seems to be very difficult. We have a lot of data. If you look at the entry 331452, you'll see links to many of these things. So a typical question is, how many little cells do you see in this picture? And this is the case of a 3x3 grid. And we have data for up to a 52 by 52 grid. We have a lot of data, but we don't have any formulas. And I know lots of people have been telling me about their new programs for guessing terms. I'd be very happy just for a guess for the formulas for this. And there are even questions about a very simple case when it's a grid with 1 by n. and there are questions there still unsolved. So last December, Scott Shannon was mentioning other kinds of problems, and I suggested that it would be interesting to look, what if you didn't divide the edges into equal numbers of points, but divided them up into a fairy division? So you remember the fairy sequence, the fairy series of fractions. For instance, the third order fairy series is 0, 1/3, 1/2, 2/3, and 1. You have denominators going up to 3 or 4. And what if you divided up the edges and you did it with a square, or you did it with a triangle, and you get some pictures, and you can ask the same question. And the reason I'm showing this is that if you look at the fairy series of order 6, you get a picture that looks pretty interesting. And this is the 6th term in the sequence 358949. It has 23,770 vertices. And the question is, what's the nth term? So Scott created this, and at the top, he classifies the points according to the number of regions. Or the degree. I thought it was the degree. Anyway, there it is, and it would be nice to have to generalize it. So the first of Scott's circle counting problems was, let's start with an n by n grid of points, and for every pair of boundary points, instead of drawing a chord, draw a circle with that pair of points as a diameter. So here's a nice picture. Here we've got 4 points. A 2 by 2 grid of points there. Oops, don't click, just point. There, 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 and there, 4 points. And for each pair of points, draw a circle with that pair of points as a diameter. And what do you get? How many regions do you get? How many circles? How many vertices? And Scott has worked out, I think, 9 terms for each of these sequences. So this is the 2 by 2 case, n equals 2. We have 5 circles, 1, 2, 3, 4, 5. The 2 opposing, diametrically opposite points give the same circle. So we don't get 6 circles, we only get 5. The number of vertices is also 5. We've picked up 1 more vertex at the center. And the number of regions is 12. If we go to the next step, we have a 3 by 3 grid, 26 circles, and so on. And the next picture looks like this. This is showing just the vertices, not the regions. This is a 4 by 4 grid, and this picture shows a 5 by 5 grid. And I described this as an astronomer's nightmare. If you were looking through your telescope and saw this, you would be unhappy. And again, we don't have formulas for any of these, not even conjectured formulas. Scott's second circle counting.
But if you have 9 terms, you can get some idea of the possible asymptotics, can you? I mean, 9 terms not that much, but still, you can get a rough idea.
Yeah, that's true. Yes, but I'd rather not have a formula. Indeed, yes. So Scott also considered the following his second circle counting problem, I'm calling it. And this is a really fundamental question. Start off with 2 points, okay? And draw 2 circles. You draw a circle centered at 1 point through the other point, and a circle centered at the other point through the first point. So you draw 2 circles. So we had A and B. We pick up 2 intersection points. We have 2 circles, and we have 3 regions. That's stage 1 of the counting. Stage 0, we just have 2 points, no circles, and no regions. Stage 1, we have 4 vertices, 2 circles, and 3 regions. So what happens? We need more terms. This is a very basic question, it seems to me, in combinatorial geometry, and maybe it's been solved, but I don't know. Here's the second stage. We've added more points, and we've got more circles, and we've got 21 regions. And here's stage 3, which already has 6,000 vertices and 7,000 regions, and I don't know how many circles there are. So
when you count regions, you're not counting the infinite region, is that right?
That's right. Yeah, I think of it as a finite graph, a finite planar graph, and just count the interior regions.
For the usual version of Euler's formula, you need to count the infinite region, though.
Well, not really. You can just ignore 1, the outer region, and subtract 1.
Fine.
So it would be nice to have more. How many circles here? All right, so the next topic I want to mention is a new version of a classic problem of how do you, what's the best way to cut up a regular polygon to make, the classic problem is to make a square. But the new problem is to make a rectangle. And so here's the classic problem. This is joint work with Gavin and Theobald. And there have been some contributions from other people, but basically it's with Gavin. And the classical problem is, I use S for square. The classical problem is, what's the minimum number of pieces you need to cut up a regular n-sided polygon to make a square? And the most famous of this problem is to cut up a triangle, an equilateral triangle, to make a square. You can do it with 4 pieces, but there's no proof known, I think, that you can't do it with 3 pieces. So that I'm calling that S of n for an n-gon. So S of 3 is believed to be 4, and let me show you. Ron Graham always used to say a talk should have a joke and a proof, and they should.
Everybody unmute yourself and laugh.
There should be a joke and a proof, and they should be different. So, but in this case, they're actually the same. So there's the joke, and the proof, the theorem, is that you can't cut up a triangle into a square using only 2 pieces. S of 3 is bigger than 2 because, and the proof is very simple, you take a square of area 1, it's got a main diagonal root 2, 1.414. The equilateral triangle of area 1 has edges of length 2 over 3 to the 1/4, which is 1.520. So an edge won't fit through the door. So you can't have a piece that has 2 vertices in it. So each vertex has to be in a distinct piece. So you need at least 3 pieces. All right. So the new problem is we don't necessarily want a rectangle, a square. We're happy with a rectangle, and you can pick your own dimensions for the rectangle.
So Neil, it's still open whether it's 3 or 4.
Yes, it's open.
Oh, very simple. Wow.
It's very simple. Yeah. Please, I wish you'd solve it. If we ask only for a rectangle, it's a little easier, obviously, because with a triangle, you only have to make 1 cut. You get 2 pieces. And if you turn over the red piece and put it there, you get a rectangle. So R for rectangle is the minimum number of pieces you need to make a rectangle out of a regular n-gon. And obviously, R of 3 is not 1, so the smallest it could be is 2, and you can do it with 2 pieces. So R of 3 is 2. So this is very unusual. We know the exact value. R of 6, for example, if you take your hexagon and cut it like that, you can get a rectangle. And surely you can't do it in 2 pieces, but I don't have a proof. So I've added these sequences, even though we don't know much about them. I've broken my own rule and added actually 3 sequences. to the OEIS with the values of up to about 12 terms for these. So this is the number of pieces for making a square out of an n-gon. So S of 4 is 1. You have your square and you don't have to do anything. And so on. And I'm actually going to mention another sequence in a few minutes, which is if you don't want a square necessarily, and maybe you don't even want a rectangle, but you want a monotile. You want something that'll tile the plane. There's been a lot of talk recently about the discovery of a monotile that'll tile the plane, but not periodically. Well, I don't care whether it's periodic or not for this purpose. So S of n is square, R of n is for a rectangle, and Q of n is the number of pieces, minimum number of pieces you need to make a monotile out of an n-gon. And obviously Q of 3 is 1 because a triangle is already a monotile. It tiles the plane. Okay, so here's an example. The reason I got interested in this problem was that a correspondent by the name of Adam Gazelman wrote to me and said that he had found some nice dissections of n-gons into rectangles, and was I interested? And I said, yeah, that's very interesting. I never thought about that, but and I came up with a few of mine. He sent examples for dissecting pentagons, sevengons, and octagons into rectangles, and that started all this work. And I spent some time on it, and then I wrote to Gavin Theobald, who is the big expert on dissections these days, who has a huge database of dissections. And he got interested, and we are just on the point of finishing up a paper about what we know, which is actually quite a lot, relatively speaking. And when I started looking at this, I came up with a 5-gon into a rectangle with only 4 pieces. And I don't think the fact that R of 5 is at most 4 had appeared anywhere in the literature, as far as I can tell, but it's not difficult to prove, and surely this isn't actually new. But anyway, here's my version. You take this pentagon and you make some cuts. These are very simple cuts. You can do it with a straight edge and compass. You don't need a ruler. And you move the pieces around. The red piece goes there, blue there, and yellow there, and you get this rectangle. So this is obviously true and seems very likely to be optimal, but there's no proof. So R of 5, R for rectangle, pentagon to a rectangle, at most 4 pieces. If you had wanted a square, then it seems you need 6 pieces. So here's a pentagon, one of Gavin's constructions of a pentagon to a square, and you can see 6 pieces. 1 piece is quite tiny, but if you only want a rectangle, you can save 2 pieces. Here's an example of a 7-gon to a rectangle in 5 pieces, and I was going to talk about that, but I think I'll talk mostly. Yes. So one thing I was very surprised to see that you can actually improve on a couple of the classic dissections. One of the most beautiful dissections ever is this dissection. Apparently it's from a 14th century Persian manuscript. You want to cut up an octagon into a square, and you do it by making cuts there. There you get 5 pieces. The blue square in the middle goes there and is rotated a little bit, and these other 4 pieces get turned around and fit around the outside. Amazingly beautiful construction. And how could you possibly beat it if you only wanted a rectangle? Well, you can. Trivially, you just take your octagon and make 3 cuts, and you can get a rectangle. So the rectangle number is 4, the square number is 5, presumably. And the same thing for the 12-gon. One of the greatest dissectors of all time was Harry Lindgren, who worked at the Patent Office in Canberra. And he wrote a great book in 1964. And one of his examples is this dissection of a 12-gon with 6 pieces into a square. Look at this. Here's the 12-gon. You copy this arc there and there, and you make those cuts, and you get 6 pieces which make a square. Lovely. But if you only want a rectangle, you can do it with 5 pieces. And I found this myself. It was surely known before, but there it is. And I've noticed in all the books about dissections, there are very few rigorous proofs that dissections work. And I wasn't really happy with that. So for our dissections, I've tried to give rigorous proofs that the dissections work. And let me just show you how you might go about giving a proof. So here's a dissection, one of Gavin's dissections. It's a dissection of a 9-gon to a rectangle. You take your 9-gon and you cut it up into pieces which fill a strip. This is a 9-gon strip. These pieces here are pieces of a 9-gon. You put them in a strip, and then this is a special case of superimposing 2 strips, but I won't talk about the general theory. Gavin builds a strip, and if you then cut a rectangle out of it, you get a rectangle. And because you got the strip from the 9-gon, you can go from the 9-gon to the strip to the rectangle. Now, to prove it's rather better to go directly from the 9-gon to the rectangle. So you cut it up and you make cuts. Again, these are straight edge and compass cuts. I won't go through them. I'll mention one. You make a cut. You cut off this chord. It's a 2 chord. A chord subtending 2 edges, and you make a cut here, which is actually this is a 4 chord, and you make a cut here. This is a 3 chord, and you look at these points, and then you draw a line here of length 1/2, and you draw a line from this vertex to the opposite side, and look at the intersection, and you get the points. And then you try to prove that you can rearrange them to make this rectangle. And here are the instructions for the straight edge and compass construction. But when you try to prove it, you prove that the pieces fit together nicely to make the rectangle, you run into some strange things. It turns out there are some distances in this picture which are miraculously equal. This distance is the same as that, and so on. There's one particular distance which appears in several different ways, and it's actually quite hard to prove that these distances are equal, because it really depends on the fact that cosine of theta is pi/11, satisfies a cubic equation. And so the proofs are quite tricky. But because it's a straight edge and compass construction, you can get exact expressions for the intersection points. If you're looking at the intersection of 2 lines, and you have coordinates for the points defining the line, then you can work out the coordinates of the intersection point, and you can do this exactly. Or you can also do it using Maple. You can do it to 20 decimal places, and you get the numbers. The trouble with doing it recursively, iteratively, looking at the intersection points, is that each further step, it makes things more complicated, so that you get enormously complicated expressions. So you can bypass that by using a different computer program, namely Wolfram Alpha. And if you can ask Wolfram Alpha, you can say, here's a number, Would you express it for me in terms of cosine theta and sine theta? Well, theta's pi over 11. And Wolfram alpha is very happy, and it will tell you, yes, that number is twice cosine theta over twice cosine theta plus 1. This number involves sine theta and a root 3. So using Wolfram alpha, you can get explicit expressions for all the intersection points. And then you can use Maple to prove Maple, especially Maple's simplify comma trig expression, will then prove that these distances are equal. And that's how you prove that this dissection works. I mentioned a third sequence, which is Q of n, the minimum number of pieces you needed to dissect a regular n-gon to a monotile. For triangles, squares, and hexagons, they tile the plane themselves. So the answer Q of them is 1. For a 5-gon, you get this rather strange-looking dissection. We want to make a monotile out of a pentagon. There's the pentagon. You make a cut here, make an isosceles triangle of edge length 1, and put it there, and then this composite piece, you can see tiles a strip, because you make copies there, and turning it upside down across there, you can clearly fill up a strip with this, and the strips fill the plane. So this is a monotile, it fills the plane. It doesn't, I'm not worried about whether it does it periodically or not. This is obviously a periodic tiling. That's fine. 2 pieces make a monotile. Gavin sent me a 3-piece dissection of a 9-gon, which is better than this problem is in Grunbaum and Shepard's famous book on patterns and tilings, and they give a number of examples, and they give a 5-piece dissection of a 9-gon into a monotile. This one of Gavin Theobald only needs 3 pieces. You take the 9-gon, cut it there, and put the 2 pieces there and there. So there's the tile. It's a monotile, and so Q of 9 is at most 3. Surely is 3. And these 3 sequences are in the OEIS.
But there's no proof yet.
No proof.
Right? Yeah.
Well, there are proofs for the entries 1, 1, 2, 1, but and that 2 and that 2, because we know that an octagon itself is not a monotile. So you need at least 2 pieces, and you can do it with 2 pieces using a very simple construction like this. This is a 10-gon, but same thing for an 8-gon.
So Q9 equals 2 is unlikely?
Yes, very unlikely, but only a conjecture.
Yeah.
So that's the end of that section. Now I want to talk about an amazing recent discovery about the.
Have you checked a lot of these constructions against Greg Fredrickson's computations for dissections?
Yes. Okay. I have all his books, and I've been in correspondence with him, and I sent him a draft of our paper.
Terrific.
Asking him, yes, you wrote those wonderful books. Do you know anything that we don't know? And he hasn't replied, so I don't know. I assume not. All right, the next section, Gilbreath's conjecture. The great Norman Gilbreath, a magician and mathematician in 1958, made the following amazing discovery. Take the primes, look at the differences between them, and look at the differences again, but actually work with the absolute values of the differences. So the absolute value of the difference between the primes is that, the absolute value of their differences is that sequence, and you keep going, and you get an array of numbers, and his discovery is that the leading column seems to be all ones after the 2. Really incredible. Actually, it turned out that this was already discovered back in 1878 by Francois Preux, who also gave a proof, which apparently is false, but still. So there's the Gilbreath conjecture. It seems to be fair to call it. These arrays are in the OEIS. The way we put arrays into the OEIS is reading them by anti-diagonals. So this whole array becomes a sequence 2, 1, 3, 1, 2, 5, and so on. And it's those 2 sequences there. Now, my colleague Andrew Odlyshko, 30 years ago, he checked the Gilbreath conjecture out to 10 to the 11th primes. And Richard Guy remarked that he only needed to look at 630 rows of this table. So it seems to me that this could now be carried out a lot further, and it would be worth doing, just in case it's not true. I don't think anyone has done it because they've been put off by seeing that it was checked to 10 to the 11th primes. But it may not be all that difficult to push it further. Anyway, so what happened was back in March, Wayman Eduardo Louis and my old friend Bob Wilson V noticed that if you take tau of n, the number of divisors of n, instead of the primes, so we do the same thing. You could do this for any sequence, write the sequence down, take successive absolute differences and look at the leading column. You could call that the Gilbreath transform of your sequence. So if you look at the Gilbreath transform of number of divisors, what you get is, well, you don't get all ones, but you only get ones and zeros. You get sequence number A361897, and you can look. And as far as I know, this is a new miracle. They conjecture that you only get zeros and ones. So I looked at some other number theoretic functions. I looked at phi of n, the Euler-Phi function, sequence A10, and there it is. And if you do the same thing, the difference is that the Gilbreath transform of phi of n seems to be 1, 0, 1, 0, 1, 0, 1, 0. Now, surely this is known to the number theorists, and maybe it even has a trivial proof. On the other hand, maybe it's just as difficult as the Gilbreath conjecture. I would very much like to know. If any number theorists listening happen to know the answer, please let me know. I also looked at a few other number theory functions. Sigma of n is quite interesting, some of the divisors. What you get, here's the Gilbreath transform of sigma of n. It goes 1, 2, 1, 1, 1, 2, 1, 0. It starts off small, and a 4 and a 3, but after a while, it blows up. You get a geyser. It goes vroom, and then it drops down. This is with the plot of 200 terms. If you look at 60,000 terms, you get some geysers, really remarkably distinct geysers every so often. And I've no idea what's going on there, what's happening. And you get a similar, even more dramatic thing if you look at the sum of the aliquot parts, sigma of n minus n. That's sequence 362452. Now, one of my favorite contributors to the OEIS for many years has been Eric Angelini in Brussels, who has a blog with many wonderful 56 with many wonderful problems. And this particular one, he called it the sum and erase problem. So here's what you do. You start off with any number, n, and you look at the initial digit, and you look at the sum of the digits. So let me do an example. 318, for example. The initial digit is 3. The sum of the digits is 12. So you write down the n followed by the sum of the digits. So that first gives you the number 31812. Number followed by, concatenated with, it's a decimal string. You think of it as a bigger number, 31812. And here's the erase part. if the initial digit 3 was a digit inside S, then you wipe out all the 3's from the number. Otherwise you don't. Well, 3 doesn't appear in the sum of the digits, so you don't make any changes. So 318 becomes 31812. Okay. But if we had started with 319, begins with a 3, the sum of the digits is 13, so we get 31813. And because the 3 is in the sum of the digits, we erase with our eraser all the 3's. So we get the number 181. Now it might happen that you get a number that begins with a 0. If n was 1019, the leading digit is 1, the sum of the digits is 11, so we get 101, 1019 followed by 11. And when we wipe out all the 1's, we get 09. And for the purposes of the OEIS, we write that as -9. But just because we can't have numbers in the OEI, non-zero numbers begin with 0. So as a signal that there's a hidden in leading 0, we put a minus sign in front, even if there are multiple leading zeros, and it's enough to have a single minus sign to indicate that.
So I'm confused about the second line. Why isn't T 31983? 13.
The second line, this one?
Yeah.
It's a typo, that's why.
Okay. Thank you.
Yeah, well, thank you. Okay, so that's the rule. So there are two relevant sequences here. First of all is what happens to n. So 0, sorry, I start with 1. This is number theory. We start at 1. 1 has the sum of digits 1, so 1 goes to 1, 1, and the 1's get wiped out and you get 0. So 1 goes to 0. The first non-zero thing is 11. 11 goes to 2. 12 goes to 3, and so on. That's the sequence 359142, and it's got some minus signs in it, obviously. The first interesting number is 11. So this was what Eric asked the world. What happens if you start with 11? Well, 11 goes to 112. 112 goes to 1124. 1124 has sum of digits 8. We get 11248. The next time the sum is 16, so we get 1124816. We kill all the 1's and we get 2486. So that's the fifth term, and so on. So he said, I have tested this for a while. What happens? And Michael Branicki, it didn't take him long. He showed that it eventually gets to 0 after 1.4 million steps, and the biggest number that he encountered had length 222. And some numbers go into cycles. Here's a cycle of length 49 that Hans Havermann found. If you begin with this number, after 49 steps, you get back to that number. And didn't I have some other? Yeah, I skipped a slide. Michael Branicki also found some other cycles. So there's an even shorter cycle of length 46 that begins with there, and there's an early cycle that begins there of length 20,000. So what happens? The question is, the obvious conjecture is that every number either goes to 0, goes into a cycle, or blows up. And is it possible for a number to blow up? If you look at what happens, if you have a huge number, the sum of its digits is going to be of order log n, and then we shrink it by the number of copies of the first digit, which probably on the average is about linear. So at each stage, it gets longer by log n and gets shorter by a linear term. So it seems the chance of blowing up is tiny. What could possibly go wrong? Could we construct a Chernobyl word which keeps growing up. I don't think you can, but it seems like an interesting question. I want to give you, my next topic is a report on the OEIS. Now, if you submit sequences, you may notice these days it often takes quite a while for your submission of a new sequence or a comment to get processed. And that's because we're very short of editors. And I've been so busy working on dissections, I haven't had time to do much myself recently. And the stack, the submissions queue, often creeps up to 300 or 400 with people who've been waiting for a month or two or more. And this is slowly getting worse. And so the board voted that we should really hire a full-time, it's a full-time job really, managing the submissions. We need a full-time managing editor, and we voted that we would try to raise money to have enough money to pay a decent salary for a full-time person to do this. So one of the initial steps was to get, in the US, we're a non-profit 501c3 public charity. We're trying to get reclassified as a 509c3 charity, which means that we will be a supporting organization for some major university. That makes fundraising a lot easier, and this is going on, and we're hoping that it'll happen this year. And once we've got that, once we're reclassified as a 509c3, it should be a lot easier to raise the money. So then the problem will be to raise the money and to find a good candidate. It'll be very complicated if the person we hire is not a US resident, unfortunately, which is a bit of a problem since we have many editors all over the world. Anyway, in the meantime, I just want to mention that you can help. Anyone can help. Anyone can go to the submission stack, and it's good to go to the end of the stack because that's where the interesting things are at the moment. Look at the submissions. You can add comments. Any registered user can add comments. Not part of the entry, but the pink box record that goes with the entry. You can say things like the definition isn't clear, or this is a really great sequence, it looks ready, it should be approved, or the sequence is wrong, this is just an erroneous version of another sequence, or very often, why do you think this is interesting? It looks like you just made it up because it's a sequence not in the OEIS right now. Why is it interesting? And so on. And 2023 is the anniversary, the second part of my report. This year is the 50th anniversary of my Handbook of Integer Sequences. So I wrote an article about that appeared in the Mathematical Intelligencer, and many people saw it on the archive. And there were articles in the New York Times and Spektrum der Wissenschaft and so on about the OEIS, and you can see these on my homepage. And here's a brief summary of the statistics. We're now up to about 365,000 sequences. We accept somewhere between 500 and 1,000 a month. We reject 40 to 50 sequences each month. We have 39 editors-in-chief and 133 associate editors. Thank you, everybody. And I like to work with a copy of this, of the whole database. There's a file called Cat25. It's an extension of the original punched cards version. You can download this and look at the whole of the OEIS as if it were on punched cards. 7.2 million lines and 500 megabytes. I wasn't sure I'd have time for this, but it looks like I do. So the final topic will be no-term, three-term arithmetic progressions. There have been a lot of wonderful talks because of the COVID pandemic in various number theory seminars, and I heard a great talk by Thomas Bloom earlier this year, who was reporting on work of Xander Kelly and Raghu Maker on one of the classic number theory problems, which is, what's the biggest subset you can have of the numbers 1 through n which contain no three-term arithmetic progression? You can't have, if you have 2 and 4, you can't have 6. No three-term arithmetic progression. And sequence number 3002 is R of n, the maximum size of a subset. And we have 211 terms of that, computed by Fausto Gariboni in 2018. And it looks like this. It's, well, there it is. And there are upper and lower bounds. The most famous lower, the classic version of this problem is Roth's 1953 theorem that if you have a subset of 1 through n that has positive density, then there's a three-term arithmetic progression. So that gives an upper bound. You can't have more than a linear. You can't have a linear function subset, or there'll be a three-term AP. So what's the biggest you can have? How does it grow with n? And then Felix Behrendt in 1946 showed that you can do pretty well if you look at if you write the numbers in base 3 and throw out the ones that contain a 2, then that set has the no three-term arithmetic progression property. So that gives you a lower bound. By the way, he was one of my professors at the University of Melbourne when I was an undergraduate, Felix Behrendt. And the news item, the reason for Thomas Bloom's talk was that these two people had reduced the upper bound a lot. They brought it down close to the lower bound, to Behrendt's lower bound. And first of all, it would be nice to have more terms of R of n. But the really interesting thing is there's a sequence that I've always been amazed by. What if you just use the greedy algorithm? Start off with 1, always pick the smallest number, which doesn't make a three-term arithmetic progression. So we can't begin 1, 1, 1, but we can begin 1, 1, 2. So we must. So this sequence, it's the greedy version of no three-term arithmetic progression. It begins 1, 1, 2, 1, 1, 2, and then 1, 1, and 4. No, I didn't get that quite right. Anyway, it's a sequence. It's well defined. It's easy to compute. We have a lot of terms. It's easy to compute millions of terms. And the graph of it has this weird fractal shape. This is a plot of the first million terms. They look like Easter Island figures. Why on earth should the greedy algorithm produce this? It would be nice to know. And what I was wondering was, how does this compare with the bounds, with Behrendt's bound, with the new bounds, and with the known values? And I just did a quick calculation, and it looks like this is giving, this is growing roughly like the base 3, Behrendt's base 3 construction. They both seem to have.
Neil?
Yes.
It's Hugo here. I'm slightly confused because I thought we were asking for what is the subset of 1 to n such that no 3 elements in the subset are an arithmetic progression.
Yes.
But then you started talking about 1, 1, 2, 1, 1, 2. That sounds like something very different.
Yeah, if the partial sums of that give you the other thing. They're very close. They're very closely related.
Okay.
Yeah. Yeah.
Thank you.
Actually, that's the end of my talk. It would be nice to know more. I think my time's up. Thank you.
Well, thanks. And let's unmute yourself and say. This ends the formal part of the talk, and Robert, please stop recording. But everybody is welcome to stay and ask Neil informal questions. And you're welcome, encouraged to put on your video and unmute yourself.